Okay, here's our topic, and here are some QR codes and buttons for you. To explain, that means you're going to need to state, uh, influence how these things are going to change the physical properties. Here's an example of what it means. I've got two liquids. Based upon their IMFs, you should be able to predict what their vapor pressure is going to be. For an analogy, we're going to use Dr. Square's weightlifting career. When he was first considering weightlifting, he knew that he increased it, certain things would go up and certain things would go down. Things that go up, he had it's a direct relationship, and the other one was inversely. Okay, so for IMFs, here are the physical properties that they will directly relate. One is boiling point. The second is heat of vaporization, melting point, surface tension, and viscosity. And the ones that have an inverse relationship are volatility and vapor pressure. And I said those out of order. All right. And I'm going to go through these with some particular diagrams. And these shapes I'm going to use are going to represent various molecules. The molecules could be um, uh, ammonia, water, ethanol or ethane, and aspirin. We're going to focus in on two molecules, water and ethanol, as I showed you before. And we're going to choose to represent the intermolecular forces with this string here. And the string is the thicker, this string can represent hydrogen bonds, or dipole, or LDS, any of the intermolecular forces. And the thicker the string, the more stronger the IMF is. All right. All right. So oh, yeah. One other thing, that's my dog. He's really kind of agitated this morning. Uh, this here, you can see that the A's molecules has got weaker intermolecular forces than B's molecules. All right. Now, all right. So boiling point, how does the intermolecular forces affect that? Well, here you can see that this molecule's got stronger intermolecular forces. That's going to keep the molecules tight and packed. Therefore, the boiling point is going to go up. That's why it has a direct relationship. So with ethanol and water's boiling point is stronger because of this. All right. Now, heat of vaporization, that's the amount of energy to change 1 mole of a gas, or so 1 mole of a liquid into a gas at its boiling point. And it's also called the enthalpy of vaporization, and that's its symbol. All right. This is also going to follow the same thing as boiling point, where the weaker the IMF, the less energy it's going to take. The stronger the IMF, the greater energy it's going to take. Here is some data to prove that. If you notice, water with its stronger IMFs has a heat of vaporization that's much, much higher. It's an incredible amount of energy. Now, melting point, here's all that's all at once. Water has a much higher melting point, or it should be ice, actually, not water. And ethanol is much lower. You can see it goes into the negatives. That's because if something's got held tightly, it doesn't want to separate from its neighbor. Surface tension is like an ability, a liquid to like stay together at the surface. And here is some water, and you're able to float a paperclip on water because of its strong IMFs. The molecules don't want to separate. Here's an image of that. If you put some drops of ethanol and water on a penny, you'll notice water can form this beautiful dome where ethanol can't. If you added any more ethanol, it would like spill over. And here are some values to show you that water's surface tension is indeed much higher than ethanol's. Almost 4 times as great. That's micronewtons per meter. The last direct relationship is viscosity. One very viscous liquid is uh, molasses, and the more surface, no, the more, the stronger the IMF, the more viscous it is. The the more of its ability to resist the flow. It's kind of a weird one because it's like a negative relationship. A viscous liquid doesn't want to flow, so the stronger the IMF, the harder it's going to be for the molecules to go to move. And here you can, if you like, molasses will stick to the side and it'll take a really long time to go back down. You can also see this with ethanol and water. If I take equal amounts and dump them, the one that spreads out the more has got the weaker IMFs because it's not very viscous. All right, there they spread out. You can see ethanol much, and then water spreads out a little bit more, but and ethanol has already begun to do something else at this point. All right, so here are my direct relationships, just as a reminder. All right, now the last two are inverse relationships. If I take some ethanol and water and dump them, I can watch their volatility. Volatility is an ability of a liquid to evaporate, and if you give them some time, you'll notice that the ethanol evaporates a lot faster. That's because of its weak intermolecular forces allows them to separate, allows the molecules to come off, like forget about its neighbor and go up into the air, be free. Whereas it's held tight, it won't do that. Vapor pressure measures volatility. All right, these are standard values at like 25 degrees Celsius. Ethanol has a much higher vapor pressure. All right, because its molecules are not held tightly, just like in volatility. So here are inverse relationships. As IMFs go up, these things go down: vapor pressure and volatility. Okay, and here are my sources for TRO. Thank you so much, and let me know if I can help you. All right, bye.